Jeremiah is going to be here talking for a brief 20-25 minutes about why you should use JSON API. We're able to do Q&A after that, and we're using a little thing called Slido. If everybody's got the app, Slido looks like this. Now, the real question of the day, this hair or this mustache, go to hashtag WeAreDevs, choose room E1, get on with that. So, in the meantime, I was reading something about you.
Oh, OK.
Now, you said you've worked for, I haven't heard of all these places.
Oh.
Thank you.
His jacket is way cooler.
Today I'll be talking about my personal grooming habits. Which is so, I haven't heard of all of these, but you say you've worked for these little places called Spotify, Fitbit, Disney, Apple.
Yeah.
And also a bunch of failed startups. And you prefer to work for companies that are both started and upped.
Yes, exactly. This is true.
Can you give us, in 3 tweets or less, what you've learned and how you've benefited from the being at the companies that actually failed?
Sure. I think the biggest thing that I've learned is how many disciplines and how many different talents are required in order for a product to succeed. When I was at Fitbit, I joined it. It was a 150 company, and then it grew to over 1,700 people over the 4 years I was there. And I was just like, why are we hiring all of these people? And it turns out you need all of those people. You need all of these different experiences. You need all of these different talents in order to make a great product.
Okay, so that's kind of the diversity argument put a different way. Just the number of brains, right, needed to solve hard problems.
Yeah.
And then you're going to come up with better solutions faster and fast enough to maybe let the thing survive.
Absolutely.
Okay, so as soon as I do this selfie,
okay,
I'm going to let you get on with your whatever it is that you're talking about. Okay, got the question in there. All right, everyone, Jeremiah Lee.
Thank you so much. All right. Again, my name is Jeremiah Lee. I am so excited to be here. This is my first time to Austria, first time to Vienna, and this is by far the biggest crowd I've ever gotten to speak to about a technology that I hold dear, which is JSON API. Today, I'm going to be talking about my experience at my previous job at Fitbit, where I led its web API for 4 years. And I know this is the headless CMS track, and I'm not going to be talking about CMSs at all. But I am really excited to see that Drupal has adopted JSON API, and I only recently got to start playing with it. And I think it's really great, and I think it's really powerful for building things other than CMSs. So my hope today is that this talk will help you understand why JSON API made sense for Fitbit's apps, and why it might make sense for yours. So often at software conferences, I hear presentations promoting a particular technology as if the only consideration of that technology is developer ergonomics. And while I do think that developer experience is really important, there's an entire software lifecycle that exists beyond the moment that we software engineers make an API request. So today, I'm going to talk about how the JSONAPI.org specification helped solve some problems at Fitbit. But this presentation is more about the problems that a large organization had working together. I've consulted with many companies on their platform strategies, and I've seen some common patterns emerge. So while I'm using Fitbit as an example, my hope is that the problems are going to feel familiar to you. And I hope to convince you that the JSONAPI.org specification will become your default style when designing web APIs. And I hope to do that through more than just technical merits alone. So it's a technical architecture that enables sustainable development practices. Now, before we get started, I do need to make one disclaimer. I no longer work at Fitbit, so some of this information is aspirational. I helped get this going, but I don't know the current state of it. Because a year ago, I moved to Sweden for my husband's job. And while Fitbit is using some of its new JSONAPI.org endpoints in production, none of those have been released on its public web API just yet. So out of the way. For those of you who are not familiar with Fitbit, Fitbit is a digital health and wellness company. Fitbit pioneered the activity tracker and the wearable space. And the Web API is important to Fitbit because it's responsible for tens of millions of dollars in annual revenue from partners. And Fitbit's own web apps, or own apps, use the exact same Web API that partners use. It handles over 4 billion requests a day. And while there are thousands of third-party apps out there, today I'm going to focus on the problems that Fitbit's own teams had building Fitbit's own apps. So let's jump into the first problem. The first problem is that Fitbit's app teams had very different perspectives on how they wanted to retrieve information from the server. Now, Fitbit has 4 major clients. It's the Fitbit app on 4 platforms. You have Android, iOS, Windows, and web. And Fitbit organizes its teams into what it calls full-stack teams. So this is the type of team responsible for an entire feature area, like exercise logging. And they have everyone that they need on that team to release a feature in the Fitbit app on every platform. So this means that the backend engineers are working directly with the client engineers on the same team to design APIs for their specific feature area. And when one of those teams would have a new feature, the team would implement it on one platform first, just a prototype. And that team was typically chosen just based on engineering availability. And then once that experience had been finalized, the other platform client teams, they would fast follow in their implementations on their respective platforms. Now, this could have worked, but Android and iOS developers have very different ideas of what an ideal web API would look like. The iOS developers, they preferred fewer network requests, and they were okay with the performance of parsing large JSON responses. But the Android developers, they preferred smaller API responses, and they accepted the trade-off of needing to make more network requests. So there was no way to reconcile this difference of opinion in version 1 of Fitbit's Web API, because the 2 biggest client teams wanted the exact opposite things of each other, because their platforms had different constraints. The second problem was that without clear guidance, the data models started getting messy. Teams were regularly overloading endpoints to make clients not have to make another API request. And so endpoints were filled with loosely related data instead of being well-scoped. And they started to resemble view models instead of well-defined normalized data models. And often that data would only be split across multiple endpoints when a new view was added to the app, because that's when the backend developers felt that they could justify another network request to the clients. And that kind of makes sense. When you go to a new screen inside of an application, you almost expect there to be some minor loading delay. So this could be fine, except that over time, the end user experiences inside of those apps evolved, and what data was needed for each of those views changed. So the data just seemed to start being arbitrarily split. There was no librarian who was keeping that data logically organized. The third problem was a misalignment between client and server data models. Clients just didn't think about data in the same way as the server. And this wasn't their fault, because the server's classes and their underlying database models, they weren't considered interfaces to the clients. And we need to remember that the I in API stands for interface. This problem was complicated because Fitbit had multiple ways that data could be expressed, such as summaries, clients of logs, collections of logs, and time series. And this problem wasn't just limited to the client and server data models, because even though the Fitbit app had a mostly consistent end-user experience across all of those 4 platforms, each platform client team decided to implement their own internal data models. And so the client teams picked different expressions of data, and they would just pluck that data from the particular API endpoint that they liked. And the clients diverged significantly in their implementations without having clear guidance on the data model. The fourth problem was that clients had great difficulty staying in sync with the server. Now, Fitbit devices, they sync with the server about every 15 minutes, but data can actually change much more frequently than that. Many people use the Fitbit app on multiple platforms, so a change made in the web app on your laptop needs to show up in the iOS app quickly. People also use third-party applications that can modify data, and then those changes from the server need to be reflected in the mobile apps and then on the device. And the Fitbit apps can also be used offline. And so when the clients would come back online, they would need to reconcile any changes that were made while the person was offline with the new changes from the server when they reconnected. So again, here are the top 4 problems that the client teams had with the Fitbit Web API. How might we go about solving these particular problems? What would the requirements look like? Well, first of all, we would need to settle the debate between the client teams over the number of requests versus the response size. We would also need an agreement on data models and how that data would fit together between the clients and the servers. We needed to create a more considerate interface. We would need some server features and an agreement on a common client approach to handling data. And we would need the ability to check if data has changed with as little overhead as possible in order to stay in sync. So let's take that first one. Now, a few years ago, we heard a lot of hype about hypermedia from API creators. And in my opinion, I think that the hypermedia proponents burned a lot of credibility because they got really excited talking about HTTP more than the problems that client developers actually had. So this made my initial discussions with about Web API design styles with the Fitbit client teams a little difficult. Because when suboptimal networks have a significant impact on the perceived and actual client performance, it's reasonable for clients to want to minimize interactions over a network. Far too many web APIs have been designed with the assumption that the clients are high-end servers with perfect network connections, but that's just not the world that mobile client developers live in. And in Fitbit case, the vast majority of web API requests were made by smartphones on hostile cellular data networks. So when the tensions are high, we need to be able to bring data to an argument. The client developers and I came to an agreement that betting on the future was a reasonable thing to do. We agreed that network performance was something getting better at a reasonable enough pace to make short-term trade-offs in order to take advantage of new advancements as soon as they became available. So we came to 3 hypotheses that we wanted to test. The first was that HTTP2 would meaningfully reduce the overhead of multiple requests. And specifically, we were looking at the binary and compressed headers with HPAC to help with that. But we were also interested in the pipelining feature because we were hoping that would make handling multiple concurrent requests easier on the clients because then the clients wouldn't need to manually handle the network connection pooling. The second hypothesis was that TLS 1.3 would meaningfully reduce the latency introduced by HTTPS because it reduces the initial handshake in half from 2 to 1 round trip. And then once that happens, you have pre-shared key session resumption and 0 round trip resumption that make subsequent secure connections significantly faster to establish if that connection gets interrupted, which often happens on mobile data networks. So this might not sound like one, just from going from 2 to 1 round trip, but the ping latency between Vienna and Fitbit's Texas data centers is 139 milliseconds, which is just above the human perceivable delay. The third hypothesis was that LTE network coverage would expand. So LTE is not only a faster connection, but it's also a more resilient connection because of its switch to packet-based networking. So we went out into the real world, and we actually tested these, and I wish I could actually share the data from those tests. But the truth is that you can now find far more rigorous tests that prove these hypotheses better than what we did. The important thing is that the affirming conclusions of these hypotheses allowed us to come to the agreement that small resources and lots of HTTP requests can be okay. Because if the responses were small, the hit for retrying the request was lower. And the faster that the response completed, the less exposure that response had to being interrupted and having to restart that request. So once we removed our fear of small requests, we needed to work on an agreement to define a common data model for those resources. So we set out and we tried to start normalizing the data, just like we might in a database. We still accepted that there could be multiple expressions of data, like the time series, the summaries, the collections of logs. But we wanted that data to be canonical and not repeated across endpoints. And in doing that, we immediately realized the need to define relationships between data. Or if you prefer a buzzword, we needed a graph. But a graph is just identifying a relationship between data and then naming that relationship. So this is the first time I'm actually going to bring up the JSON specification, because it sets explicit instructions on how to define and name relationships between data. And here's how one of its creators, Yehuda Katz, defined it. JSON API is a wire protocol for incrementally fetching and updating a graph over HTTP. Let's break this down. First of all, JSON API is a wire protocol. So that it means it includes both a format for data resources, as well as a specification of operations that you can do on those resources. JSON API works incrementally, which means that clients can fetch data as they need it at the appropriate granularity. JSON API defines a way for both fetching and updating, because modifying resources is often just as important as fetching them. JSON API defines a graph structure, which really just means that it's a way of linking data together in a well-defined and easy-to-use way. And it works over HTTP, which means that JSON API uses the HTTP protocol, including its caching semantics, as its backbone. So let's see what a JSON API style API actually looks like. Here's the response for a social feed post. Now, most of this content is in the attributes object. There's also relationships defined, such as for the user who authored the post. So after fetching the newsfeed post, the client could then fetch the user information, since it is a distinct type of data. But let's go back to that client use case. It's reasonable to assume that there will be situations where clients will need a newsfeed story and the related user author information at the same time. So while a client could get the initial resource and then go fetch the related resources, that puts a lot of work on the client to get the response, parse it, get the relationship URL, request it, and potentially have to do that multiple times. So the JSON specification has a way of dealing with this use case, and it's called compound documents. It allows clients to include multiple related resources in the initial resource request to avoid having to chain together multiple requests. And it works simply by adding the include URI parameter for the relationship. But now we're back to that problem of having potentially large API responses that contain a whole lot of data that we just don't need. This is an example of an exercise summary. There's a lot of data that could potentially be requested just in the summary for an exercise. So once again, JSON API provides a solution to just getting what we need, and it's called sparse field sets. It's a standardized way of allowing clients to request only the pieces of data that they want. You add a fields URI parameter with the resource type, and then you explicitly specify the desired object properties. And sparse field sets also work when you're requesting a compound document. You would simply include the name of the relationship and then the fields on that relationship that you want. So this allows you to keep your data well organized while also keeping the API responses lean. Now, one of the challenges was not just getting the clients to agree on common data models, but getting them to agree on a common way of retrieving, storing, and presenting data. Now, this part is not related to the JSON API.org spec, but JSON API's approach to data enables clients to improve the perceived and actual performance of the end-user experience. So here's an example of a life cycle for how clients benefit from sharing a common approach to handling data. This first example is for fresh data. The view is going to request data from the client's local database, but the database isn't going to have it. So it's going to go fetch the data from the web API. This is going to be a cache miss because it hasn't ever retrieved that data before. The database will then save the response from the server, which will then cause the view to render. But if that data did already exist in the database would return that data to the view immediately. And then simultaneously, it would ask the web API if that data was stale. Now, if the data hasn't changed, nothing else happens. And the user just saw an immediate display of data with no downside, because caching works. It's really great. But if that data is stale, as soon as the header response returns a 200 instead of a 304 not modified, the view can be triggered to display an updating state. And when the body of the web API response finishes coming in, it can get stored in the database, which will then cause the view to render with the updated information. So again, the key detail here is that the data model is mostly shared between the clients and the API because it is a considered interface. So that resolves number 3, which leads me to the requirement of fixing client-server sync. Now, the caching semantics of HTTP provide an excellent foundation for checking if data is outdated or not. Resource caching is a feature that's been used in web browsers for decades now, but it's been less common in API clients. So we effectively introduced a resource caching system for API clients when we defined that common approach for retrieving and handling data. Well-defined normalized resources also have an additional benefit. They improve cacheability. Because if a change affects fewer data resources, then there will be fewer resources invalidated when data changes. That just makes sense. And because all the clients are now accessing data in the same way, we don't need to put data in multiple places. JSON API leverages the caching semantics built right into HTTP, but it does require a small shift in thinking. So this is an example of fetching an image from a server. When the resource is returned for the first time, there's an e-tag header that's sent along in the response. And when the client wants to request this image again from the server, it sends the previously returned e-tag in the request. And that's what allows the server to respond with 304 not modified if the image hasn't changed. And then the client can load that image from the local cache instead of downloading it over the network again. But with the JSON API response, the e-tag is not returned in the header. This information appears in a meta object. The e-tag for a JSON API response can't represent the exact bytes of a response because a request might have used a JSON API feature like sparse field sets or compound documents. So instead, we put the e-tag in a meta object to represent the version of every resource and relationship returned in a response. It still gets passed in the if-none managed header on a follow-up request, and you would still get a 304 not modified response if the state of the resource hasn't changed, which will save you on your data transfer. So let's put all of this together. What does this actually look like in practice? Well, here's an example of the Fitbit user profile screen on the iPhone 10 app. Now, there are 2 API requests that I want to focus in on here. It's a request for the profile information, such as my name, biography, country, URLs for images, and then also a request for my friends list collection. Now, the noteworthy thing about both of these API requests is that they are both highly cacheable data. Most people don't add and remove friends regularly, so who's in my list of friends doesn't change that often. And most people don't update their profiles that often, so the profile data is with my list of friends and the active user also doesn't change that often. So this means that most of the time when people view this screen, the data display is immediate, and it's not refreshed after the first render. And only tiny API requests and then not modified responses are sent, which really saves on data transfer. Now here's the Fitbit dashboard screen. This is a real-time summary of your day. And this is an example of the exact opposite caching scenario. Most of the data on the screen is not benefited from caching. You're constantly burning calories just sitting here and being alive. So even if you haven't moved since the last time you opened up the Fitbit app, you will have burned more calories. The data would be invalid. Now there is some data on the screen that benefits from caching, such as your sleep data. Once you view it for the day, it's not going to change unless you manually edit that sleep log or take another nap. But this is a good example of why you would want to have separate API requests, because the data that hasn't changed gets a quick not modified response. Now the Fitbit newsfeed is a great example of data with mixed caching scenarios. Most of this data is ephemeral. That'd be the newsfeed stories. People are unlikely to see the exact same content more than once because new content is always being generated, and data that is infrequently accessed doesn't benefit from caching. However, the stories have related content that is likely to be repeatedly accessed and therefore cached. It would be the story's creators, your friends. So if there are 20 newsfeed stories that are created by 15 of your friends, that would mean that the client could save downloading 5 friends' basic profile data multiple times. And if the user had just viewed the friend leaderboard prior to opening the newsfeed, the app would not need to re-download any of the friends' basic profile data. So this is a nice performance benefit from having normalized data with defined relationships. And you can start to see how it adds up across multiple experiences inside of an application. Now you might be thinking, why didn't you just use GraphQL? Well, if your API use case is the same as Facebook's, which is GraphQL's creator, it might be great for you. GraphQL actually works really well for APIs that are read-heavy and don't benefit from caching because the data is either not repeatedly accessed or it's not modified frequently. GraphQL is great for scrolling through an endless news feed, where you'll see a story once and never again. But in my experience, that's the least common API use case. So GraphQL doesn't provide a notable advantage to most API providers. And I know GraphQL has gotten a lot of attention because of its developer ergonomics, but developer experience is not more important than end-user client performance. I'll say that again. Developer experience is not more important than end-user client performance. And there are other standards, like JSON API that I've talked about today, as well as OData, that provide similar developer experiences to GraphQL while actually enhancing the client performance for the most common use cases. For starters, the main benefits that people actually like about GraphQL can be obtained using sparse field sets and compound documents, which don't require developers to embrace an entirely new tool chain because the features in JSON API are completely optional and they're easy to unlock by adding URI parameters. And the biggest area of performance consideration, in my opinion, is caching. And that's out of scope for GraphQL. GraphQL does not leverage the built-in caching features of HTTP, and it does not have a common suggested way for caching. So if a developer works with multiple GraphQL-based APIs, they'll likely need to learn and accommodate multiple caching methods. And I believe that caching is just too important of a client performance consideration to be an afterthought. Another common use case not addressed by GraphQL is pagination. JSON API specifies how clients should use pagination and collection access. And it does that by providing next and previous links to clients as URIs, and clients simply request that. So this enables the client to just grab the data from the URI because it allows the server, and that allows the server to specify the pagination strategy. And that's one of the few areas when designing APIs where it's really hard to hide the database implementation details. But pagination in GraphQL is done by the client. And this is really unfortunate because it makes it very easy for clients to make very expensive database queries using offsets. And I'm not going to get into the details of cursor strategies for pagination. But this just shouldn't be something that clients have to worry about. And again, I think this use case is too important and too common to be an afterthought. And lastly, this is probably the biggest one, I believe in the inherent advantage of clients and servers sharing a common data interface as much as possible. Reflective input and output makes composing create and update statements from the client much easier when that data model is shared. And if you have data that is not only write-heavy but also modification-heavy, GraphQL mutations can become complex quite quickly. So JSON API specifies a way of doing updates and creates, but it also works extremely well with an adjacent specification called JSON patch. And JSON patch allows for incremental, lightweight modifications and even streaming updates, which is pretty cool. So in conclusion, I hope I've convinced you to consider JSON API for your next web API. While I do think that GraphQL is an advancement in API design, I think that the JSONAPI.org specification better addresses the concerns of client developers as well as performance for end users. And I hope I've convinced you that making suboptimal networks less painful for client developers and the end users is something that API design styles can help with. And I hope that I've convinced you that designing data models with intent and study of client needs is not a step that can be skipped. GraphQL and JSON API give clients control over what data gets returned in an API response. But that does not mean that highly intentional API design does not need to happen. So that's all for me for now. There's a few other features that I didn't get to talk about in this talk. There's also really great tooling available for every major app platform and framework if you want it. The best part is that clients don't need to use them when using a JSON API-based API because they can just add some parameters on. So go check out JSON API, and don't hesitate to reach out to me on Twitter if you have questions or create something cool with it. Thank you so much.
So thank you very much.
Yeah, thank you.
one of the big questions, we have probably time for just one. I think you give a lot of very reasonable reasons why to use JSON API instead of GraphQL.
Yep.
But what about when someone comes in and uses a GraphQL client like Apollo? Does that balance this out in any way?
Sure. So Apollo is a great product. It still requires an integration. You still have to do work in order to take advantage of it, you know? And Apollo has done a lot of really great things, specifically on the caching front, that are beyond the base spec.
Yeah.
So you do get a few more things by using Apollo, but Apollo is just one particular GraphQL implementation.
But JSON API out of the box gives you all of that stuff,
Right.
and I don't have to worry about it.
Right. Any server or client that's complying should have those features built in.
Okay, thank you so much. That was really, really interesting.
It's been great.
Jeremiah Lee, everyone.